March 15, 1944. Eglund Air Force Base, Florida. The Bell P59 Era Comet sat motionless on the tarmac, its twin jet engines silent, while technicians struggled with a problem that threatened to ground America's first operational jet fighter. The aircraft's primitive radar system, housed in a metal nose cone, had failed for the third time in 2 weeks. Metal housings created interference patterns that rendered the radar nearly useless. The electromagnetic waves bounced chaotically off the metallic surfaces, creating blind spots and false readings that made the system more dangerous than helpful. Standing beside the grounded fighter, Dr. Robert Dicka, a young physicist from MIT's radiation laboratory, examined the failed radar housing with growing frustration. The war effort demanded reliable airborne radar, but conventional materials seemed fundamentally incompatible with the electromagnetic requirements. Metal conducted electricity, creating interference. Wood absorbed moisture, warping under flight conditions. Canvas tore in high-speed flight. What America's radar program desperately needed was a material that didn't exist yet, something transparent to radio waves but strong enough for military aviation. The solution would emerge from an unlikely collaboration between a small boat manufacturer in Massachusetts and scientists working on classified military projects. Within 18 months, this partnership would accidentally create one of the most versatile materials in industrial history. A substance that would revolutionize not just military radar systems, but eventually transform civilian boats, home construction, automotive manufacturing, and dozens of other industries in ways its inventors never imagined. The mathematics of electromagnetic transparency were about to intersect with the chemistry of synthetic polymers, creating a material that would shape the modern world. The crisis in radar technology had been building since 1943. American aircraft manufacturers were installing increasingly sophisticated radar systems in bombers and fighters, but the metal nose cones required for structural integrity created electromagnetic shadows that crippled system performance. The SCR-720 Airborne Interception Radar, standard equipment on night fighters, lost approximately 40% of its effectiveness when housed in conventional aluminum fairings. German radar operators had learned to exploit these blind spots, timing their approaches to avoid detection. Allied bomber formations suffered increased losses because their radar operators couldn't distinguish between friendly aircraft and enemy fighters approaching from certain angles. The Radiation Laboratory at MIT, established in 1940 to develop radar technology, had assembled the finest collection of physicists and engineers in America. These scientists had solved seemingly impossible technical challenges, miniaturizing radar systems that once required entire buildings into units that fit inside aircraft. They had developed magnetron tubes that generated microwave radiation with unprecedented power and precision. They had created display systems that translated electromagnetic echoes into visual images pilots could interpret instantly. Yet they remained stymied by the fundamental incompatibility between electromagnetic waves and the materials available for protective housings. Dr. Luis Alvarez, who would later win the Nobel Prize for his contributions to particle physics, led the team investigating radome materials. His laboratory notes from early 1944 revealed the depth of their frustration. Every conventional material failed in some critical way. Metals created interference patterns that destroyed radar effectiveness. Ceramics shattered under the stress of high-altitude flight. Plastics available at the time lacked the strength and durability required for military applications. Traditional materials simply could not meet the contradictory requirements of electromagnetic transparency and structural integrity simultaneously. The breakthrough began in an unexpected location. Beetle Incorporated, a small company in Littleton, Massachusetts, had been manufacturing wooden boats since 1935. Ray Green, the company's founder, had built a modest business creating sailing dinghies and small motorboats for the recreational market around Boston. The company employed fewer than 20 workers and occupied a single building beside the Assabet River. Green had no background in chemistry, no experience with military contracts, and no knowledge of radar technology. His expertise lay in traditional boat-building methods passed down through generations of New England craftsmen. Everything changed when Green received an unexpected visit from Dr. Dicka in April 1944. The MIT physicist had heard through contacts in the Boston area about Green's experiments with a new construction technique. Rather than building boats from separate wooden planks joined together, Green had been experimenting with continuous fiberglass cloth, saturated with synthetic resin. The technique promised to eliminate the seams and joints that made wooden boats prone to leaking. Green had developed the process purely for commercial reasons, seeking to build stronger, more durable small craft for the civilian market. Dr. Dicka examined Green's experimental boats with the trained eye of a physicist, rather than a maritime enthusiast. The fiberglass and resin construction created a continuous surface without the metal fasteners that characterized conventional boat building. More intriguingly, the material appeared to be largely transparent to electromagnetic radiation. Dicka borrowed samples of Green's fiberglass cloth and polyester resin, returning to MIT for electromagnetic testing that would change both of their lives forever. The test results exceeded every expectation. Fiberglass cloth saturated with polyester resin demonstrated remarkable electromagnetic transparency across the frequency ranges used by military radar systems. Unlike metal, which reflected electromagnetic waves, or wood, which absorbed them, the fiberglass composite allowed radio waves to pass through with minimal distortion. The material also possessed structural properties that surpassed conventional radome materials. It was lighter than aluminum, stronger than wood, and completely resistant to moisture absorption that plagued other composite materials. Within weeks, Dr. Dick had convinced his superiors at the Radiation Laboratory to fund a classified development program with Beetle Incorporated. The small boat manufacturer found itself transformed overnight into a defense contractor working on one of the war's most sensitive projects. Ray Green, who had never built anything larger than a 16-foot sailing dinghy, was suddenly responsible for manufacturing radar housings for advanced military aircraft. The technical challenges of scaling up from boat hulls to aircraft radomes required innovations that pushed both companies beyond their existing capabilities. Aircraft radomes operated in conditions that no boat would ever experience. At 30,000 feet, temperatures dropped to minus 40 degrees Fahrenheit. Air pressure fell to less than one-third of sea level values. Flight speeds approaching 400 miles per hour created aerodynamic stresses that could shatter inadequately designed housings. The electromagnetic requirements demanded precise control over material thickness, fiber orientation, and resin chemistry that boat building had never required. Green's small workforce, suddenly expanded to over 100 employees, learned to manufacture components to tolerances measured in thousandths of an inch. Traditional boat builders accustomed to working with hand tools adapted to precision manufacturing techniques borrowed from aircraft production. The company installed temperature-controlled curing ovens, precision measuring instruments, and quality control systems that exceeded anything previously seen in the boat-building industry. Workers who had joined expecting to build recreational sailboats found themselves creating components for classified military applications they weren't allowed to discuss with their families. The first operational fiberglass radomes were installed on modified P-61 Black Widow night fighters in September 1944. The results immediately validated years of theoretical work and months of intensive development. Radar performance improved by 60% compared to metal-housed systems. The lightweight fiberglass construction reduced aircraft weight by 40 pounds per installation while providing superior aerodynamic characteristics. Most importantly, the electromagnetic transparency was so complete that radar operators reported the housing seemed invisible to their instruments. News of the successful radome program spread rapidly through classified channels to other military applications. The Navy requested fiberglass housings for shipboard radar systems. The Army Air Forces wanted larger radomes for ground-based installations. Each application revealed new capabilities and sparked additional innovations. The material that had begun as an experiment in small boat construction was proving adaptable to applications its inventors had never contemplated. By early 1945, Beetle Incorporated was producing over 200 radomes monthly for various military applications. The company had grown from 20 employees to over 400. Ray Green had transformed from a small-town boat builder into the head of one of America's most important classified manufacturing programs. Yet, even as military production reached its peak, both Green and Dr. Dicka recognized that fiberglass composites possessed capabilities that extended far beyond radar housings. The war's end in September 1945 should have meant the collapse of Beetle Incorporated's military contracts, and a return to building small recreational boats. Instead, Ray Green discovered that peacetime applications for fiberglass composites seemed limitless. The material's combination of strength, lightness, and resistance to corrosion made it ideal for applications that traditional materials couldn't handle. Within months of VJ Day, Green was fielding inquiries from industries that had nothing to do with boats or radar systems. The first unexpected application came from the agricultural sector. Farmers in New England had heard about the new fiberglass material through word of mouth and wanted to know if it could solve problems with traditional farm equipment. Wooden grain storage silos rotted within a few years, especially in the humid climate of the Northeast. Metal silos rusted, requiring constant maintenance and eventual replacement. Could fiberglass provide a better solution? Green's engineers, now experienced in working with complex three-dimensional shapes, designed experimental grain silos using the same techniques they had developed for aircraft radomes. The results impressed even the skeptical farming community. Fiberglass silos proved completely resistant to moisture, vermin, and the chemical reactions that destroyed other storage materials. They weighed less than metal equivalents, making installation easier, and their smooth interior surfaces prevented grain from sticking or spoiling. By 1946, Beetle Incorporated was manufacturing agricultural storage systems alongside their continuing boat production. The construction industry provided the next major breakthrough. Architects and builders had long struggled with the limitations of traditional building materials in harsh environments. Coastal construction faced constant assault from salt air that corroded metal and rotted wood. Industrial facilities dealing with chemical processes needed materials that could withstand exposure to acids and caustic substances that destroyed conventional materials within months. Dr. Benjamin Phillips, a chemical engineer from DuPont who had worked on wartime polymer research, visited Green's facility in late 1945. Phillips had been investigating applications for synthetic resins in construction materials and was intrigued by reports of fiberglass composites. What he saw at Beetle Incorporated convinced him that fiberglass could revolutionize building construction in specific applications where traditional materials failed consistently. The collaboration between DuPont's chemical expertise and Beetle's manufacturing experience produced innovations that neither company could have achieved independently. DuPont's chemists developed new resin formulations optimized for construction applications rather than electromagnetic transparency. These resins cured more slowly, allowing workers additional time for installation, but created stronger bonds with fiberglass reinforcement. Beetle's engineers designed manufacturing processes that could produce large flat panels and complex architectural shapes cost-effectively. The first major construction application emerged from an unexpected source. The United States Navy, still operating numerous coastal installations built during the war, faced enormous maintenance costs from salt air corrosion. Metal structures required repainting every few years. Wooden buildings rotted and required constant replacement of damaged sections. The Navy's Bureau of Yards and Docks approached Green about manufacturing building panels that could withstand marine environments indefinitely. The naval construction panels developed in 1946 demonstrated capabilities that astounded traditional building contractors. Fiberglass panels showed no deterioration after months of exposure to salt spray that would have severely damaged other materials. They required no painting, no sealing, and no regular maintenance beyond occasional washing. The panels were lighter than equivalent wooden construction, stronger than most metals in specific applications, and could be molded into complex shapes impossible with conventional materials. Word of the Navy's successful fiberglass construction projects spread through the building industry faster than Green could expand his production capacity. Chemical plants wanted fiberglass panels for areas exposed to corrosive substances. Food processing facilities needed materials that wouldn't contaminate products or harbor bacteria. Swimming pool manufacturers discovered that fiberglass created smooth, non-porous surfaces that traditional concrete couldn't match. Each new application revealed additional capabilities and sparked further innovations. The smooth surface of fiberglass panels made them ideal for applications where cleanliness was critical. The material's resistance to temperature extremes made it valuable for both refrigeration and high-temperature industrial processes. Its electrical insulation properties, originally discovered during radar housing development, proved useful in electrical equipment enclosures and power generation facilities. By 1947, Beetle Incorporated employed over 800 workers, and operated 3 separate manufacturing facilities. The company had evolved far beyond its origins as a small boat builder, becoming a diversified manufacturer of fiberglass components for industries ranging from agriculture to aerospace. Ray Green, who had started the decade building wooden dinghies, now oversaw a manufacturing operation that supplied materials for applications he had never imagined. The residential construction market provided the next major expansion opportunity. Home builders in hurricane-prone areas had long struggled with materials that could withstand extreme weather conditions. Traditional roofing materials failed under high winds and driving rain. Siding materials warped, rotted, or corroded, depending on their composition. Insurance companies were increasingly reluctant to cover homes in areas prone to severe weather unless they incorporated materials proven to withstand extreme conditions. Fiberglass offered solutions to many of these problems, but required modifications to make it suitable for residential applications. Home construction demanded materials that were not only durable but also economical enough for widespread use. The precision manufacturing techniques developed for military radomes were too expensive for civilian housing. Green's engineers worked to develop simplified manufacturing processes that maintained the material's essential properties while reducing production costs. The breakthrough came from studying the insulation requirements of residential construction. Traditional insulation materials like mineral wool or cellulose provided thermal resistance but often settled over time, creating gaps that reduced effectiveness. Moisture infiltration could destroy the insulating properties of many materials, leading to energy waste and potential structural damage. Fiberglass insulation, manufactured as continuous batts rather than loose material, promised to solve both problems simultaneously. The development of fiberglass insulation required solving manufacturing challenges completely different from those encountered in boat building or radome construction. Insulation needed to be lightweight, flexible, and manufactured in long, continuous rolls that could be easily installed between wall studs and ceiling joists. The fiberglass fibers had to be much finer than those used in structural applications, creating a material that trapped air effectively while remaining easy to handle during installation. Working with insulation manufacturers who understood the residential construction market, Beetle's engineers developed processes for creating fiberglass batts that maintained consistent thickness and density. The material proved superior to traditional insulation in virtually every measurable characteristic. It didn't settle over time, maintained its insulating properties even when slightly compressed, and was completely resistant to moisture damage that destroyed other insulation materials. The first residential installations of fiberglass insulation occurred in 1948 in homes built for returning veterans under various government housing programs. The results exceeded every expectation. Homes insulated with fiberglass required significantly less energy for heating and cooling compared to houses using traditional materials. The insulation maintained its effectiveness year after year without the gradual deterioration that characterized other products. Most importantly for homeowners, the material paid for itself through reduced energy costs within a few years of installation. The success of residential fiberglass insulation created demand that overwhelmed Beetle Incorporated's manufacturing capacity within months. Orders poured in from construction companies across the country as word spread about the material's superior performance. Home builders who had initially been skeptical about this unfamiliar product became its most enthusiastic advocates after witnessing dramatic improvements in energy efficiency. The company that had struggled to produce 20 boats per month just 4 years earlier now faced the challenge of manufacturing millions of square feet of insulation annually. Ray Green recognized that meeting this unprecedented demand would require fundamental changes in both manufacturing processes and business organization. The precision techniques developed for military radomes were completely unsuitable for high-volume residential products. Insulation manufacturing demanded continuous production methods that could operate around the clock while maintaining consistent quality across massive quantities. Green's engineers worked frantically to develop automated systems that could produce fiberglass batts at speeds that hand manufacturing could never achieve. The solution emerged from studying textile manufacturing processes used in cotton and wool production. By adapting machinery originally designed for spinning natural fibers, Beetle's engineers created systems that could draw molten glass into continuous filaments, thousands of times finer than those used in structural applications. These ultra-fine fibers, when collected into batts and treated with binding agents, created insulation with thermal properties that surpassed anything available in the residential market. The manufacturing breakthrough required innovations in glass chemistry that pushed the company into entirely new technical territories. Traditional fiberglass used borosilicate glass formulations developed for laboratory equipment and optical applications. Insulation manufacturing demanded glass compositions optimized for fiber drawing rather than optical clarity or chemical resistance. Working with glass manufacturers who supplied the container industry, Green's team developed new formulations that could be drawn into consistent fibers while maintaining the thermal and moisture resistance properties essential for building applications. By 1949, Beetle Incorporated operated 5 separate manufacturing facilities dedicated exclusively to insulation production. The company had licensed its technology to manufacturers across the country, creating a network of production capacity that could meet national demand for residential and commercial insulation. Each facility employed between 300 and 500 workers, many of them women who had developed exceptional skill in operating the complex machinery required for consistent fiber production. The expansion into insulation manufacturing had unexpected consequences for the building industry itself. Architects and engineers suddenly provided with insulation materials that maintained consistent performance characteristics, began designing homes with much higher energy efficiency standards. The availability of reliable thermal barriers allowed builders to experiment with construction techniques that had been impractical with traditional materials. Passive solar heating, previously limited to experimental structures, became feasible for mainstream residential construction when combined with high-performance fiberglass insulation. From a grounded jet fighter with a failed radar housing to millions of American homes staying warm through winter, fiberglass had traveled an extraordinary journey. Ray Green's small boat shop beside the Assabet River had accidentally created a material that would define modern construction, proving that innovation often emerges from the most unexpected collaborations between necessity and ingenuity.